In this video, we're going to talk about comparison tests. There are two types of comparison tests. First, the direct comparison test, and second is the limit comparison test. The direct comparison test says that suppose that infinite series of A of n and B of n are series with positive terms. If the infinite series of B of n is convergent and A of n is less than equal to B of n for all n, then the infinite series of A of n is also convergent. So basically what this is saying is that if we know that the bigger infinite series converges, then we know that the smaller infinite series will also converge. And if the infinite series of B of n is divergent and A of n is greater than or equal to B of n for all n, then the infinite series of A of n is also divergent. So this basically says that if the smaller infinite series diverges, then we know that the bigger infinite series also diverges. Let's take a look at some examples of direct comparison tests. Let's take a look at this infinite series. What would you compare this series with? Well, this looks like a geometric series. We know that this infinite series converges because by geometric series test, because the common ratio, which is 1 over 2, absolute value of common ratio is less than 1. Now, which one is bigger? 1 over 2 to the n plus 1 or 1 over 2 to the n? Now remember, if the numerator is the same, the one that has a bigger denominator is less than the other. So we know that this is less than or equal to 1 over 2 to the n. So what can we conclude? The bigger series converges, therefore the smaller series converges by the direct comparison test. So this series converges by the direct comparison test. What about this infinite series? What can we compare it with? We could compare it with 1 over n, where this is the harmonic series with p equals 1. Therefore, this infinite series diverges. Now, which one is bigger? In this case, this is bigger than 1 over n because this one has a smaller denominator. So what can we conclude? The smaller diverges, therefore the greater diverges as well. So this infinite series diverges by the direct comparison test. Now, in order to see whether this infinite series converges or diverges, you want to compare it with this series. Again, this is a harmonic series, therefore this diverges. Now, 1 over n plus 1 is less than or equal to 1 over n. So this is a bigger series, and this diverges. So what can we conclude about the smaller series? By the direct comparison test, this is inconclusive because if this is a smaller series and diverges, then we could say the bigger series diverges. However, in this case, this series is bigger than that series. Therefore, we cannot use the direct comparison test. And we have to use different tests for this infinite series. Now let's talk about the limit comparison test. Suppose that you have two infinite series that are with positive terms. If limit as n approaches infinity of A of n over B of n equals c, where c is a positive finite number, then either both series converge or both diverge. So what happens when we get 0? Test is inconclusive. You cannot apply limit comparison test. And what happens if it goes to infinity? Same thing. You cannot apply limit comparison test. Or when the limit is undefined. So the limit comparison test fails when we get 0, infinity, or undefined after you go through the limit process. Earlier we looked at this infinite series and we found out that when you compare it with this harmonic series, the direct comparison test failed because the bigger series diverged, so it didn't say anything about the series that is smaller. So let's use a limit comparison test. It's limit as n goes to infinity of 1 over n plus 1 over 1 over n. By the way, we know that this series diverges. So what happens? You get limit as n goes to infinity of n over n plus 1. And as n goes to infinity, you get 1, where 1 is a positive finite number. So since this diverged, we know that, and we got a C that is a positive finite number. They both diverge since this diverged. So by the limit comparison test, we know that this infinite series diverges. What about this infinite series? What would you compare it with? I would compare it with the infinite series of 1 over n squared, because we know that this is a p-series and it converges by p-series test. So how would you set it up? You say limit as n goes to infinity of 5 over 2n squared plus 4 over n plus 3 all over 1 over n squared. So you get limit as n goes to infinity of 5n squared over 2n squared plus 4n plus 3. So what happens as n goes to infinity? Well, you could apply L'Hopital's rule or just compare the degree and the coefficient. They have the same degree and the coefficient is 5 and 2. So you end up getting 5 over 2. Or you could apply L'Hopital's rule. You get the same result. Now 5 over 2 is finite and it's positive. Therefore, what can we conclude about this series? Since this series converged, they both converge. Therefore, this infinite series also converge. Again, if this goes to 0 or infinity, then comparison test fails. So be careful. Now let's take a look at this infinite series. What would you compare this series with? Well, you got 3n on top, you got n cubed. So just ignore the 3 for a second. This is like n over n cubed, which is like 1 over n squared. So you want to compare with this p-series, where we know that this series converges by p-series test, because p is 2. So let's do the limit comparison test. Limit as n goes to infinity of 3n plus 2 over n cubed minus 2n all over 1 over n squared. So you get limit as n goes to infinity of 3n cubed plus 2n squared over n cubed minus 2n. As n goes to infinity, they have the same degree. Let's compare the coefficient. You get 3. Or you could apply L'Hopital's rule and you will get the same result. 3 is positive and finite. So what can we conclude about this series? They both have to converge because this series converged. So by limit comparison test, this infinite series converges. Now let's take a look at this infinite series. What would you compare this with? Let's see what happens when you compare this series with this harmonic series, which we know that this series diverges because the p is equal to 1. So let's do the limit comparison test. So what happens as n goes to infinity? Well, that goes to 0, and that goes to 0 as well. So it's 0 over 0, which means that we could apply L'Hopital's rule. So let's apply L'Hopital's rule. You get negative 1 over n squared times cosine of 1 over n over the derivative of 1 over n, which is negative 1 over n squared. And these two cancels out. So what happens as n goes to infinity? Cosine of 0, which is 1. And this is a positive finite number. And since we know that this series diverged, this series also diverges. So this series diverges by the limit comparison test. Again, note that the limit comparison test fails when you go through the limit process and you get 0, infinity, or undefined.